Hello guys, KNOCKCAT this side. So today we are yet with another problem, and that is kth common ancestor in a binary search tree. So the problem statement says that we are given a binary search tree with n greater than equals to 2. That means we have at least two nodes, and we need to find the kth common ancestor of nodes x and y in the given tree. And if the kth ancestor does not exist, we need to return -1. Also, it says node x and y will always be present in our input BST, and x is not equals to y. That means they both are distinct. So if I look to the very first case, um, if you see 20, so 20 is somewhere here and 30 is here. So if there is a common edge above and the node which is an ancestor of both, ancestor means parent or grandparent or great grandparent. So if so for a node to be an ancestor of some node, it has to be its ancestors. And ancestors are, let's say, on the above level, which are parent, grandparent, um, so like above nodes. And P and Q are to be descendants. So these are two terms. So descendant are actually said to about children, grandchildren, great grandchildren. So for a node to be an ancestor of some nodes, or like let's say two nodes, because this is a BST, so binary search tree, so we cannot have greater than two nodes. So for for a node to be the ancestor of two nodes, so then both the nodes have to be the descendant of that node. That means they should lie on the lower levels, and descendant means they should be both of the nodes should be having a either parent or a grandparent, or either one is parent and one is grandparent relation. So let's say if I would have say, tell me the lowest common ancestor of let's say 30 and let's say 50. So if you see some any node for which both of these nodes are descendants, so we can see for 10, see this edge, like you will draw this, so you will be able to relate it what actually we need to tell. So this is a very first node who having descendant both P and Q. So this is our first ancestor, or we can say the lowest common ancestor. Similarly, if I had have said, tell me of 20 and 30. So if you draw these edges and find a node which has relation to both of the nodes, or which is ancestor to both of P and P and Q are both descendant to that node, then this 40 is there, and this is we can say an LCA, that is lowest common ancestor. If I look to the second example, and randomly if I say you, tell me of 70 and 30. So there's one more property of ancestor that of related to lowest common ancestors, that a node can be an ancestor to itself. Okay, a node can be an ancestor to itself. So 30 can be its ancestor, and we can see 30 and 40 have 30 and 70 have a parent-child relationship. So in this case, 30 is the lowest common ancestor. So a node can be its own ancestor. Okay, तो ये होता है. Similarly, if I say you tell me of 70 and this 70, then you will like try to draw a common edge where both of the nodes where like the path of both the nodes are merging. So you have to find that first node where paths of both two nodes are merging. So if I have drawn till here only 40, so then these would have never connected. So if I have joined that both paths are merging, so 80 is the first node which is an ancestor to both of the nodes. It's not about a single node, to both of the nodes. Okay, so 80 is here the ancestor. Again, if I ask you, tell me for 40 and tell me for 60. So similarly, you will again draw these paths like this. So you can see 80 is again the first node which is having ancestor descendant property to both the nodes. So this is about lowest common ancestor. And unfortunately, I would say these examples, this says that it is a BST, but these are not BST actually. Because in a binary search tree, what happens if this is a node, on the left hand side, the nodes are lesser, and on the right hand side, the nodes are greater than the parent node. Similarly, if I have this node here also, on its left, it would be less, and on its right, it would be greater. And this single property holds for entire subtree. That means for this node, all the nodes in its left subtree would be smaller. And if let's say there would be an right subtree, so for this node, the entire right subtree would be having nodes greater than the root node, because on the root nodes are greater than the parent node, and on the left nodes are lesser than the root node. So here you can see 10's left should be smaller, but it is greater. So this is example is not a BST. Again, yes, they say about BST, but this is actually not a BST. 80, 70. You know, if some nodes follow the property that left node should be lesser than the parent node and right node should be lesser than the parent node, can there be a case that both two nodes are equal in a tree? Think by yourself that if all nodes follow the property that nodes on the left side should be smaller and nodes on the right side should be smaller. So let's say if it was 8, 6 it should be like, let's say 6, and it should be greater, let's say 10. 6 left, it has to be less, so let's say it should be 3. It has to be greater but less than 8, so let's say 7. And similarly it is 10, so let's say 10, it has to be smaller but greater than the 8 because it is on the right subtree. So 10, you can say 9 is the only value we can have, and here let's say 15. Can you find it if all the nodes follow the property that left has to be smaller and right has to be greater? Can there would be two nodes which have same value? It cannot be the case. In BST, we cannot have duplicate values. So these test cases are actually wrong. But still, they say the height of the time complexity height of BST. That means BST has a use it here. The images might be wrong, but I think the test cases works for the BST logic. So we will, because I approach the BST logic only and not the trivial uh, ancestor, like not the trivial LCA, but using the BST property and it works. So, and since the problem is also about like in BST, so we can actually use of some properties. But yes, these examples don't support because these are not BSTs. So let's come to the whiteboard. It's a general introduction that what is actually a BST and that I have already discussed that they have at most two children, and the left child and right child, with the left child containing values less than the parent node, left child less than the parent node, and the right child containing values greater than the parent node. So this is it. So I'm not taking those examples because those examples will be difficult to understand because they were not a valid BST. Again, a lowest common ancestor is defined between two nodes P and Q as the lowest node in tree that has both P and Q as descendant. As I actually said, both P and Q has to be descendant of some node. Okay, so now I am taking an example to understand you the intuition and logic. So like let's take this example. So let's say you need to find like let's say something is Q and Q and you need to find its lowest common ancestor. Uh, Firstly, we'll find lowest common ancestor. In the question, we have to find the kth one. Okay, but first I will talk about how can we find a lowest common ancestor in a BST. Okay, I'm not talking about the trivial. I'm talking about in BST. In BST actually. So let's say nodes, if some nodes are have to be descendant of some node, like because in ancestor two nodes have to be descendant, and descendant means they are on the lower, let's say lower levels. That node has to be on lower levels because if these two nodes are descendant and some node has to be their ancestor, so in a tree it is very intuitive that these that node would be at higher levels. Do you agree with this? That if two nodes are descendant to some node, so that node is actually at higher level than those nodes. So if I'm talking about P, some nodes P and Q, they cannot reside on the same level. There might be a possibility that they can reside on the above level, but they cannot reside on the same level. Okay, this thing is clear. So if I say, tell me of like 25 and 35 and 35. So if I had to find their ancestor, it would be at some place which would be above them. And since it is a BST, can I use the logic of BST? Like in the left subtree, all values should be less, and on the right subtree, all values are greater. So if I can say that, let's say I'm at root, let's say I'm at root, can I say like this, that if you are at root and both of P and Q lies on the left subtree, both P and Q lies on the left subtree, so can I say that you can actually move left? Because we need to find the lowest common ancestor, the lowest one. So this is one of the case. Like if P and Q are both smaller than my root node, that make sure that both P and Q lies in the left subtree. So if I'm at 40 and I need to find for these P and Q, and here we can clearly see, yes, 25 and 35 both are less than 40. So yes, I can actually move to left subtree. Why? Because both are lesser. And BST says that left nodes at the left are smaller. So, and since both are smaller, I can actually move my root to here. So I came to here. Now I am at a root where 25 is less and 35 is greater. Where 25 is less and 35 is greater. So it do not follow the property that both the nodes are lesser than the root node. So can you think that yes, not, if both nodes are not lesser than uh, the root node, that means one node is in the left subtree and the other node is the right subtree. Can you say it as a right ancestor? Because yes, this is a very first node uh, over where left there is value at left and there is value at some value at right. And since we cannot move down, we cannot move more downwards, because if we have to move left, then both the values should be appear in the left subtree. Or if we have to move right, then both the values should be appear more at the right subtree. And since in this case, we can see that we cannot move because 25 is lesser and 35 is greater. That means it is intuitive type of intuitive that we know that it resides somewhere above, and now one is at left subtree and one is at right subtree. Okay, so this is the very first case. Also, there can be a second case where both the P and Q are on my right subtree. Both the P and Q are on my right subtree. So, can I actually check? Let's say I have to find out 45 and 60. Can I say, yes, I'm at 40. Tell if 40 is lesser than my P and Q, that means my P and Q reside on the right subtree and I can move my root to here. Yes, this is also true because now I know this is a BST and both of my nodes resides are greater. That means these both nodes are greater than my root, and that means they both lies on the right subtree. And since I am looking for a lowest common ancestor, I should move close to those nodes. So I come to right. And when I came to 50, this is a similar situation uh, like the prior example where I move left, and now I check that is 45 and 60 are greater than 50. So we can clearly see 45 and 60 are not greater than 60. Neither 45 and 60 are less than 50. Because if that's the case, I would have moved left. Or if both are on the right subtree, then I would have moved right. But since here I can again see that no, one follows and one don't follows. For moving to left or for moving to right, both should be either small or both should be either greater. So I'm at a point where uh, both of the properties don't applicable. So that means yes, 50 would be the node over on its left subtree there would be P, and on its right subtree there would be Q. It has to be that case. So now you might be thinking that it would be of always this case. So it can be of this case. Let's say I'm at 50 and I said okay, move left, so it would be greater values. And let's say there are some values, let's say 55, because it has to be less than 60 but greater than 50, and let's say this is 65, and now let's say 50, it is 51, 55, it has to be 52, let's say, and I ask you about 51 and 52. Okay, 51 and 52. So now you can see 51 and 52 are greater than my root node. So can I move to right? Yes, I would move to right because both this is very sure that both exist on the right subtree. So I came here 60. Now I check 51 and 52. They both are lesser values than my root node. That means they both resides on the left subtree. Yes, I came to left. Now I'm at 55. Okay, take this value as 58. because 52 it has to be greater. Now we came to I 55, and here 55 is not greater than both 51, and 51 is also not greater than both 58. So this is actually not true for both. So that means one lies on the left subtree and one lies on the right subtree. So we can say 55 is our lowest common ancestor. Now we have find the lowest common ancestor, and we have to find the kth common ancestor, kth common ancestor. So can we actually say that if some node is an ancestor of both the node, if some node is the ancestor of both the node, can I say that the node which is above to it, the node which is above to it will also be an ancestor to both the nodes? If this node is ancestor to both the nodes, can I say the parent of this node, which is 60, would also be an ancestor to both the nodes? Yes. And similarly, can I say if 60 is the common ancestor, the node which is above 260, which is actually 50 here, this would also be the lowest common ancestor for this? Like, let's say, what I'm saying, if parent is an ancestor to these nodes, if parent is an ancestor to these two nodes, then parent's parent will also be the ancestor to these nodes. This, like, let's say this is a reflexive property. If a parent is a ancestor to both of the nodes, then parent's parent will also be an ancestor. Then this grandparent will also be an ancestor, and then this great great grandparent will also be the ancestor to both the nodes. So that's how we can actually find the kth one. So for this 51 and for this 52, we know that 55 is lowest common ancestor. And if 55 is lowest common ancestor, then 55's parent should also be its ancestor of these P and Q. Yes. And then 60 also comes from somewhere. So if 55 is, so 60's parent will also be an ancestor. And at some point, by iterating above, like this has to be ancestor, let's take this color, this has to be ancestor, this has to be ancestor, and at some point I will come to root. Because if some node is ancestor, so nodes above, which are parent of that nodes or which are ancestors of that LCA, would all be the lowest common, which all will be the ancestors of these P and Q. So at some time I will reach to root. So can we actually say that from the lowest common ancestor, to the path till root, all the nodes would be the common ancestors of P and Q? Yes, we can say the same thing, because if this is the, then reflexive property says that this will also be the ancestor, and not reflexive property that I gave a math intuitive logic, but in diagrammatically, or we can see that if this is also, so this also is an ancestor. Though reflexivity is a proof to this, but in diagrammatically it is very clear that yes, if this is it, so this is also an ancestor to both of these P and Q. So we can say till from this LCA, lowest common ancestor to root, all the nodes should be the common ancestors. So if you understand till here, we have like actually claimed this problem now. Now the problem says that we need to find the kth common ancestor. Now we need to find the kth common ancestor, and that is the kth common ancestor. You can clearly see the nodes I get from here is one ancestor, two ancestor, and third ancestor. I'm getting first ancestor, second ancestor, and third ancestor. So if k value is greater than these all nodes, like we have three here, and if k happens to be greater than three, that means lowest common, kth common ancestor does not exist. But if k is less than the nodes which I get from the path from root to the lowest common ancestor, then we can return the kth one. So now the problem becomes simple. Let's say I got this path from my root to LCA. I will retrieve the path from root to the lowest common ancestor. And now, if I can find reverse it from LCA to root. So this one will be the first LCA1. It would be somewhere like LCA1, then LCA2, then somewhere till root. So if these all nodes are less than or like less than k, or like if these nodes are till k, then I can actually return the kth ancestor. If it is up to k, I can return kth ancestor. But if k is greater than the size of this path, then we cannot have, that means kth ancestor does not exist. So now let's move to the part, uh, one small summarization. Since this is a BST, so and if there is some ancestor to some nodes, then intuitively it has to be above both of them because it is either its parent or either its parent to one or grandparent to one, like this. So we can actually say that if that node lied on the left subtree, then we can actually move left because we are finding lowest one. Okay. And if both the nodes resides on the right, then actually we can find right. But at some point, if we don't move, we can don't move to the left or we cannot move to the right also. That means neither both the nodes lie on the left subtree and neither both of the nodes lie on the right subtree. That is a very clear indication that one of them is on left subtree and one of them is right subtree. That means that node is the first or the lowest common ancestor of the given two nodes. And if that node is an ancestor, all the nodes above till root will also be their ancestors reflexivity, and you can say if parent is ancestor, then grandparent is also ancestor. So we can get these nodes. And now, if the size of this path is up to k, we can return the kth ancestor greater than k or less than, sorry, if it is greater than k, we can actually return, but if it is less than k, we cannot return. So minus one case. So that's all about the approach. And now let's move to the coding part. So let's come to the code. Let me first reset this. So okay. So first thing, we need to find the first or the lowest common ancestor. So let me call one function. Let me call one function lowest common ancestor. I think this is visible. Okay, this lowest common ancestor. So I pass root, and since I need to find the lowest common ancestor for x and y, and let's say I take it in an LCA. So I will find the LCA. So let's say now I have find the LCA, the lowest common ancestor. After that, the second step. This is the first step. After that, I have find the lowest common ancestor. The second step is actually what? We need to get all the nodes from all nodes in the path from root to LCA. That is first lowest common ancestor. Because similarly, if this is an ancestor, this has to be ancestor. So I need this path. Okay. So let's say I would call a function here, and let's say get path is a function, and I need to find from root to LCA. So let pass root and let pass LCA. Also path called a path matrix, which will help me in storing path. Okay. So now I will get the path size. So if k happens to be greater than path dot size, that means, and that path is actually or the number of ancestors which would be in the path matrix are lesser than k. So if it is lesser than k, if I have five nodes which are ancestors and I need to return the eighth one, so can I return? I cannot. So this case is return minus one, or else we can just return path of k minus one because it is a zero base index. So this is our actually third step. So now we should write the code for the lowest common ancestor. So it is of node type. The function is lowest common ancestor, and we know that we passed root x and y. So that is node star, let's say root, integer x and integer y. So what we said, the two properties. So first case would be the simple trivial case that if we are at some point that does not exist, that if our root becomes null, we can just say return null ptr. In that case, our lowest common ancestor would not exist. But here the question says that x and y will always present. So this case would not be of the probability to come, but still we write, so we are writing. So now I said that if x is less than my roots data and y is also less than my root data, the similar thing, that means my both p and q resides on the left subtree. So to the I can move to the recursively I can move to the roots left. I think this step is clear. If both are in the left subtree, I should move to the left subtree. And if both are greater than my roots data or like roots value, then I can actually move to the right subtree. So I just move to right. And if none of if they don't exist to the left and they don't exist to the right, that means that root is our lowest common ancestor. So we just return root. So this helps us to find the lowest common ancestor. Although this is a BST, the problem says this is a BST, then only this logic is actually would work. Otherwise, the question that is actually help that the logic that actually help in finding lowest common ancestor is a slight different. But since this is a BST, so we can actually use these conditions. That either if it is resides on the left subtree, both values, we can move to left, or alternatively we can move to right. So this is how I find the lowest common ancestor. And now I need to retrieve my path from root to LCA. So let's say void type get path, and what we have here, we have our root and LCA. So node star root, node star LCA, and vector of int and path. So we know the value for LCA, and if I know LCA value, so I can actually traverse my tree in that fashion, because if LCA is on the right subtree, that means I need to move right. Same like BST. If I want to find this 20, and let's say this is not this is 30 actually, then it would be BST. So I need to find 30 and I'm at 10. So 30 is greater. So I know the path would contain 10 and the path would move to its right because 30 is greater than 10. So I came to 40 and 40 is also an ancestor. Now 40 will say, okay, for 30, are you less than me or greater than me? 30 is less than 40, that means it resides on the left subtree. And similarly, we came to 30. And now 30 is our LCA, so we can break. So I can traverse just on the behalf of value because this is a BST. So can I write just iterative code? Although we can write iterative code here only, but here I write the recursive and here I would be writing the iterative so that you can actually understand uh, how iterative works and how recursive works. So recursive one is fine, like if this valid, then it would be on the left. So we call towards left, otherwise we call towards right. And if none of them matches, we return root. So here we need to retrieve the path. So can I do like this? That while my root data is not is equals to my LPS data. Okay. So not equals to. So that first node would be, we know that this first node would be our part of the root. Root has to be our part of the LCA. Okay. Root has to be part of our LCA, or if they are equal, then like although if root is our first LCA, then it's fine. Then this condition will not work. But if that's not the case, if first LCA is lowers the root level, then it has to be pushed back. So that means if they are not equal, this path is definitely my LCA. And now I can move simultaneously that if my LCS data is greater than my root data. If it is greater, then I can say root is equals to root side. Just I will move my root side. Else, that means my LCS data is less than root's data. That means it resides in the left subtree. So I can just say root is equals to root left. And similarly, at some time, root's data would become equal to LCA data, and this while loop will got break. And since this while loop got break, so when its both values become equal, that LCA first, that lowest common ancestor value didn't come into our vector. So I can just say at the end, path dot pushback LCA's data or root's data, because now my root is pointing to the LCA node. So that's how we get the path. And third step was if k is actually greater than my path dot size, return -1, others return path k of -1. This part can also be done with recursively, but like I did recursive, you can actually write the same thing. That if this happens, just call like this root right call, and otherwise just call this root left call. But I did iteratively so that you can get the gist of both that, because this is a BST and we know either it has to be on the left, either it has to be right. So we just have to move our root accordingly. So can be done with iteratively, can be done recursively. So let's run this and see if there are any errors. So okay, it says lowest common ancestor I pass was not declared in the scope. Okay, so lowest I make it capital, let's make it small, and I think now this is fine. First step is like we find the LCA. Second step is we find all the nodes from root to LCA, and okay, I should reverse them. And why I'm reversing? Like that makes my job easy because I explained here that when I will take the path from root to LCA, when I will take the path from root to LCA, they would be in this fashion. They would be in this fashion, like from root to LCA. But LCA first node is this, second is this, third is this. So and I need to return the kth one. So first, second, and kth will be in this. So if I make this reverse, then I would actually get from LCA to root, and that makes my job easier, and I can just return k minus one. Otherwise, you can do like iterating from behind and things like that, but that makes it complicated. So why when we can do a reverse, so we should do. Okay. So so 40 is coming. Let's submit this and hopefully it works. So it is working, and I tell you the whole three steps. And some might be thinking that this would be order of n of reverse. No, this would also be order of height of tree. Uh, Not this. So let's discuss for the time and space complexity. Since we are doing a BST traversal, so we know that we need to find P and Q. And at some step, we are moving either right, either left accordingly. Either left, either accordingly. We are moving to left or right accordingly to our values of P and Q. That if they reside on the left sub tree, we are moving left. If they reside on the right, we are moving right. So at first, it's not like we are covering all the end nodes. Yes, it's not the case that we are covering all the end nodes. So we can just say we will actually go the height of BST. We will actually travel for height of BST. That means worstly I can traverse like till here for finding my P. Worstly, because let's say my P is here and Q is here are on the last nodes like P and Q, and before that there are thousand of nodes which follows. So at worst I only traverse the height. The height. We are not traversing the whole tree. So we are traversing only the height of BST. So that's why this part is height of BST. And now also we are getting from LCA to root to LCA. From my root to LCA. And this will also be the height of tree at worst. Why? Like if these are 40, so this will also be a height of tree because here also we are following the same property. Either move to left, either move to right, either move to left, either move to right. We are not iterating the complete tree. We are just traversing one path that either move to left, either move to right. So this is also a height of tree. And now, since like if we traverse the height of a tree only, so then there is never the case that this path matrix will contain n nodes. They cannot contain n nodes. So this will also contain height of nodes contain only which are onto the equal to the height of BST. Like in this case, if height is like 2, so they only contain two nodes because this is the first ancestor. So overall, the time complexity would be this order of height of BST only, and since the path matrix only can contain height of BST nodes, so the space complexity is also height of BST. So let me write the time complexity. It will be height of BST only, or you can say log of n, although not always, but it's more convenient to say height of BST. And space I tell because at max it can contain on that path, it can only contain it would traverse till that path only. So these path nodes, and that is actually the height of BST. So space complexity is also the height of BST. So that's all about the problem. And don't be confused with the example test case. Like these are actually wrong the diagrammatically. Although if this is not following the like BST logic, then this would have not worked. So since it is working for the BST and we can move accordingly left and right, so that's why I feel the internet excuses are working fine. So that's all about the problem, and I hope you get to learn something from this. And but just focus on these three steps, and you are done. Also, you can actually work on this without reversing because you know you have nodes from root to path, and you need to find the kth one. So you can iterate from behind, or you can find the index from behind and just return it. Then you don't need to reverse. So that's all. And thank you, and knock at this side.